In this video, what we're going to do is summarize some of the thoughts that we developed around how symmetry, how the geometrical shape and sort of regular properties of the system with regard to geometry can help us solve problems a little more easily with certain kinds of mathematical tools. So these came into play when we were thinking about the electric field with regard to Gauss's law. So namely, Gauss's law is this integral of the electric field over some area. It's basically the electric flux through a closed surface. And that's related to exactly how much charge is enclosed in a system divided by epsilon 0. Now, there's a couple of things that were really important to be able to use Gauss's law. And in this course, what we found that was important was that, one, that the electric field was parallel to the dA vector, that is, that it was perpendicular to the surface everywhere, and two, that the electric field magnitude was a constant over the surface. If we were able to say both of those things, this dot product became much more simplified, namely that we would end up with a magnitude of the electric field integrated over some area is equal to the enclosed charge divided by epsilon 0. That's when Gauss's law is useful. Now, this statement of Gauss's law is always true. It's just not always applicable because we can't always get to this. So if we think about like a plus charge sitting somewhere, what we would often do is draw a Gaussian surface around it. And the electric field we would know is perpendicular to the surface everywhere or parallel to the area vector everywhere. And as a result, the electric field times the surface area of that sphere is equal to the total enclosed charge divided by epsilon 0. This gives us a really quick way of deriving the point charge formula. We did that for a couple of other distributions, right? We talked about surface charges on a plane. We talked about a line of charge and so forth. But what we're doing here is we're exploiting the symmetry, the geometry of the situation using these two principles, or these two ideas, namely that E is parallel to dA and E is constant over the surface. A similar mathematical tool that we developed was called Ampere's law, and that was for magnetic fields. And that one was slightly different in that instead of a surface integral, what it's looking at is an integral along some path of the magnetic field is equal to the total enclosed current times mu naught. And so if we were to look at it in the exact same way, what we would say is, well, what we need everywhere is first that B is parallel to dl everywhere on the path that we're choosing. And the other thing that made it really nice was when the magnitude of the magnetic field was constant along the line. If those two things were true, we ended up with a very simplified result, namely that that dot product became the magnitude of the magnetic field integrated over some path is equal to the total enclosed charge times epsilon 0. Now again, Ampere's law, always true. We can always write this down, but not always be able to use it to calculate the magnetic field. We have to be able to satisfy these two things to be able to use it effectively. So what we did for that was we had often a line current that had some current running down it. And so we could take an Amperian loop that went around the whole thing because we know the magnetic field goes around the wire. And so at any location, let's say S, the magnetic field is parallel to dl. It's parallel to the loop the whole way around, and it's exactly the same magnitude. So as a result, what we get is the magnetic field times 2 pi times S is mu naught I. And so we have a very quick way of writing down the magnitude of the magnetic field due to a long wire that didn't involve the Biot-Savart law. So what these two laws help us to do is to exploit the symmetry, the geometry of the problem, to simplify our result. Now, in both cases, we have to have properties that we can say or argue are true, which is namely that the field itself is sort of parallel to the thing that the dot product's being taken over, whether that's dl in Ampere's law or dA in Gauss's law, and that magnitude of those fields is constant over either the circulation loop or the surface area that you're integrating over. If you can do both of those things, you get a much more simplified description of this integral, and therefore can solve for the field much more simply.